In this lecture, I'm going to cover divergence and curl, which is the expansion, contraction, and rotation of a vector field. So we've covered the path, we've covered a scalar field, and now we have a vector field. Picture it like water. So first, let's plot it. A vector field maps from n dimensions to m dimensions, but the easiest way to think about it is just from 2 dimensions to 2 dimensions, 3 dimensions to 3 dimensions. So here we have an example of f maps using the mapping x squared, y squared. So what does that look like? So what I do is I put in different values of x and y and get out a position. So what I have here is 0.00 goes to 0, 0. 0.01, which is this point here, 0.1. It doesn't go to 0.1. It goes from there up 0.1. Yeah. And then 0.2 gets mapped to 0.4. So that means from 0.2, it goes up 4 spaces. And similarly, 0.-2, it goes from 0.-2 up 4. Yeah. But actually, it isn't really up 4 because every single point, the length, the reason why we have the length is kind of the speed of the movement towards that direction. Let's take the example of the diagonal. Let's take the point 1, 1. 1 squared gives you another diagonal, so it goes along the diagonal. 2, 2 gives you, once again, along the diagonal. So it's telling the magnitude and the direction it's going. But if you put this all together, because a vector field is every point, it's everything. Here we are representing it like as little vectors, but there could be many more. And we see a vector field. It's like a flow field. It's like the wind. You think of it like that. So here's another one. Y plus x, xy. You see there's different shapes in there. You see there's a turning part. There's a bit of a turn here. There might be some contraction and expanding out of flow. And similarly with the previous one, we think, oh, we have loads of flow going up this way, with flow going this way and this way and this way. And you could draw on these for ages. Oh, and you have a bit of rotation here and a bit of rotation here. And, you know, that's what the weather forecast people do. But they are motivated, and we have cosine, another one that oscillates up and down. But that's my descriptive. But using mathematics, I can have a formula that tells you exactly what's happening at each point. So here we have Da Vinci illustrating how complicated flow can be. You have loads of rotational stuff here. Rotation, rotation, rotation. You have some more rotation here. So loads of rotation, quite complicated. What about expansion? You have water coming out of a pipe, and it can come out in many different ways, and it goes in and causes rotation. So you can have rotation, expansion, and contraction. Flow can be complex. A vector field that represents this flow can be quite complex because you have different contractions and expansions and rotations at different locations in the flow field. And this is exactly why we use derivatives. We use divergence to describe the expansion and contraction. We use curl to describe rotation. And all this is motivated by our gradient. This video here is really lovely at visualizing these things. So, gradient, just a quick recap. The gradient is the vector of derivatives. The I is the x derivative, the y derivative in 2 dimensions. In 3 dimensions, we have x, y, and z, I, j, k. Yeah. So why we say that is because each of these, the divergence and the curl or rotation, are motivated by the gradients. And we apply the vector operations we learned to them. So the first one is divergence. This is a dot product. So every vector field can be rewritten as some function for the x direction, some function for the y direction. Yeah. And the divergence is the gradient, which is our derivative in the x direction I plus derivative in the y direction j, dot the original vector field. And that just gives the summation of 2 derivatives. And that gives you a value. And that value is a magnitude. You have to remember that. Divergence expansion is how much is expand, how much is contract. It's a number or a formula for a number at a different point, at each point. And 3 dimensions expands out. The vector field has an x part, a y part, and a z part. And our divergence is derivative in the x direction by x, derivative in y direction by y, derivative in z direction by z. And that gives you your divergence. So let's apply it. Oh, and in n dimensions, it's the same kind of premise. So let's do a couple of examples. In example 1, x, y, z, x, y, 0. We don't really care about the z part because I want to be able to plot it. This is what the plot looks like. It's expanding out. No, I'm already preferring what's happening. It's expanding out like a geyser from the middle. Yeah, flow feet expanding out. So we have our vector field, we have our formula. So let's break it down. First, we get df dx, which is just x. Fx, which is x. And we differentiate with respect to x, which is just 1. Our y component is just y. We differentiate that with respect to 1. And we get our answer. The divergence is 1 plus 1, which is 2. And that means it's positive, so it's an outflow. It's expanding. Yeah. Here we have a rotational one. Once again, I'm going to ignore the z part. But you see it. It's moving like that. But if something's just spinning around in orbit, is there expansion and contraction? No, unless it's disturbed. Once again, let's work our way through the example. fxy is equal to minus yx. So the fx, the x directional part is minus y. The derivative of that with respect to x is 0. The y directional component is just x. Derivative of that with respect to y is 0. So our divergence here is 0 plus 0. So there's no inflow or outflow. It's equal, so it's just 0. It just stays rotating forever, like the orbit of something. And note, if I put a dot here, it'll just flow around in a circle. That's what it's saying, around and around and around. That's what we have with our flow field. Our next example, so you see it, and you're automatically, you're drawn to the middle. Everything's just flowing into the middle. It's contracting. So let's see the mathematics. Fx is equal to, that should be minus x. Derivative of that is minus 1. Fy, that should be minus y. Derivative of that is minus 1. And so our divergence is minus 2, which means there's inflow. So the plus means expansion, minus means contraction. That's it. Nothing more interesting than that. Our last example. We have our vector field xy, which is x plus y, xy. Yep. So as I said before, this is complicated. You can't say, is that expanding there? Is that contracting? What's happening? So we do the differentiation. fxy is equal to x plus y, xy. fxy, x plus y. And we take the derivative of this with respect to x, which just gives us 1. Fy, the y direction component, is a combination of x and y. Derivative of that is x with respect to y. So now our divergence is 1 plus x. Now, what it's saying is, when x is minus 1, there's no divergence. Now, it's not that immediately obvious to see, but that's meant to be along that line. But what we have to the left of that line is when x is less than minus 1, minus 2, it's contracting. And when it's greater than, it's expanding. But really, all you have to say is there's expansion and contraction at different locations. Now, we've talked about expansion and contraction, which is divergence, and now we get to curl. Curl is how a fluid rotates. The direction of the curl is the axis of rotation as determined by the right-hand rule. So always going back to your right-hand rule. So how does it rotate? What does it rotate round? Yeah. And the magnitude of the curl is the magnitude of rotation, the speed of rotation. If the vector field represents the flow of velocity of a moving field, then the curl is a circular. So it's how it rotates. A vector field whose curl is 0 is called irrotational. This will come up in 2 lectures' time, and it's an important note. So how do we calculate it? Divergence was dot product, curl is cross product. So what we do is we take our original vector field and we do a cross product. And note, this part will always be the same because it's always been the cross product of the gradient. And this is what we change each time, this x, y, and z. The answer is always a vector because a vector says where it's rotating. So if you have a vector field that's pointing out like that, it means it's rotating around this. That's what it means. So when you do your cross product, you get your smaller matrices, and then you expand them out to get this form. Now, note, there is nothing here that is df dx. So there's no derivative of the x direction component with respect to x. There's no derivative of the y component, the fy, with respect to y. Everything is mismatched, just as a reference there. Yeah. So that why I mean that that's a z, that's a y, that's a y, that's a z, that's a z, that's an x, that's an x, that's a z. Note that it's a pattern, yx, xy. Yeah. So maybe that'll help a bit. Now, let's go through some examples. The same as before, but now we're looking at rotation. So does this expanding flow look like it's rotating? No. Now let's see if the maths agrees. So what we have here is our vector field, and we just take it into 3 parts, the x part, the y part, and the z part, and place it into our matrix. Yeah. Now we have to do a bit of differentiation. For the x part, we differentiate with respect to y, so the derivative of x with respect to y is 0. Derivative of x with respect to z is 0. The y part, fy is y, that's that part. Derivative of that with respect to x is 0. Derivative of that with respect to y is 0. Fz is equal to 0. So the 2 derivatives there are 0. So now we bring it all together. Okay, here we are at derivatives that we just calculated. That's our general formula. And we just place each of these into the answer. Yeah, so fz dy goes in, so that is 0. Fyz is 0, so those go in. Next is those 2, and lastly are those 2. And so what we have is 0i, 0j, 0k. There's the vector of rotation is length 0, so there's no rotation. And that's what we have here. That's a summation of it. No rotation. Now, example 2, we immediately see that it's rotating. Yeah? We see it flowing around the flow field. That's a very bad circle, but that's what it looks like. So let's see if the maths agrees. Like before, we just state what our x component is, what our y component is, and what our z component is. Our x component is minus y component is x, z component is 0. We put it into our matrix, and then we calculate. So firstly, let's differentiate the x component, the x part, which is minus y with respect to y, and then z. Derivative of minus y with respect to y is minus 1. Derivative of minus y with respect to z is 0. The y component is equal to x. So derivative of that with respect to x is 1. With respect to z is 0. And lastly, z is 0, so derivative is all 0. So once again, they're the elements we need, and we plop them into this formula. So we have our fy, fzy, fyz, and we put it all together. Yeah, and so that makes 0 in the I direction, 0 in the j direction, and plus 2 in the z direction. And that just means it's rotating around the z axis. That's it. That's everything brought together, and it's clockwise rotation around the z axis. So now we have example 3. So immediately you see example 3, there, as we've from the divergence, there's inflow, but there doesn't look like any rotation. Let's see what the mathematics shows. So, like before, we have our flow field and we take the x component, the y component, and the z component and put it into our curl formula. We take the derivatives. Derivative of minus x with respect to y is 0. Derivative of minus x with respect to z is 0. Derivative of minus y with respect to x is 0. Derivative of minus y with respect to z is 0. So this is all 0. So once again, that immediately goes, nothing is happening here. We take those formula and we put them into, and we get 0. So this has no rotation. It has contraction, but no rotation. Our last example, the more complicated one where it's kind of going, hey, there's something here, maybe there's something there. What's happening? Yeah. So let's set it up. We have the x component is x plus y. The y component is xy, and the z is 0, just for simplicity's sake. We put that into our curl formula, and we take the derivatives. So the first point, the f part is xy. Derivative of that with respect to x is 1. Derivative of that with respect to y, z is 0. The y is xy. Derivative of xy with respect to x is y. Derivative of xy with respect to z is 0, because there's no z. And just the 0, z is all 0 as before. So we've done our calculations. We have our formula, and we just put the values in. And what we have is a vector that is not I, not j, and 1 minus yk. So this is complicated because what you have to do is you have to put in values of y to find out the rotation part. So what does it look like? Rotation direction changes for different values of y. Yeah. So if I put y is equal to 0, so that's y is equal to 0. Well, maybe let's do y is equal to minus 2. If y is equal to minus 2, we should have some clockwise rotation. If y is plus 2, we should have an anti-clockwise rotation. Yeah. Anti-clockwise and clockwise. But as y changes, you change between clockwise and anti-clockwise. Also, the magnitude of it changes as well. The further you are in the y direction, the larger the magnitude of the rotation, the faster the rotation. So let's bring it all together. Example 1, it was just x, y, and the z component was 0. That had a divergence equal to 2 and a curl of 0. So what do we know? This vector field has expansion, but no rotation. That's how you sum it up. The next one is minus y x 0. That had a divergence of 0, but a rotation of not I, not j, minus 2k. So it has a rotation around the z-axis, but no expansion or contraction. Now, minus x minus y, z is 0, where my head is. So that gives us a divergence of minus 2, a rotation of 0, 0, 0. So there is contraction, but no rotation. And lastly, x plus y, xy, and 0 for the z part. This had a divergence of 1 plus x. So the divergence changed from expansion to contraction for different values of x. And a rotation or a curl of not I, not j, 1, y minus 1k. So that field has both expansion, contraction, and rotation. So it's complex. And that's what I'm looking for when asking, what does the flow field look like? These kind of broad statements are what I'm looking for. In the next lecture, I'm going to introduce Jacobian, which is another way of doing this, talk briefly about the Hessian, and sum up all our differential calculus.